Hey everyone, and welcome back. This is the third session of Chapter 3 in our AI Fundamentals course. Today, we're going to pull back the curtain on an AI technique that's working for you every single day, probably without you even noticing. It might seem like magic, but once you see how it works, you'll be blown away by its clever simplicity. All right, let's get into it.
We've all seen this, right? An email promising you a fortune, a miracle cure, or a prize you never even signed up for. The second it lands in your inbox, you just know something's off. But have you ever stopped to wonder? How does your email service, out of the hundreds of messages you get, instantly know to send this specific one straight to the spam folder? It feels like magic, but it's actually a brilliant piece of probabilistic AI at work. And today, we're going to solve that exact mystery.
To crack this case, let's meet our main character, the Naive Bayes Classifier. Now, I want you to think of it less like a complex algorithm and more like a detective. A slightly naive detective, maybe, but an incredibly effective one.
So what's the official definition? Well, it's a machine learning technique for sorting things into categories. In our case, the things are emails and the categories are either spam or legitimate emails, which we call ham. The key here is that it learns by studying thousands of emails that we've already labeled as either spam or ham, figuring out what makes them different.
Now, why do we call our detective naive? Because it makes one huge, simplifying assumption. In reality, we know that word order and context are crucial for meaning. But our classifier naively assumes that every single word in an email is an independent clue completely unrelated to the words around it. It sees an email as just a big bag of words, ignoring grammar and structure entirely. Now, that might sound wrong, but that naive assumption is actually its superpower. It allows it to be incredibly fast and efficient, focusing only on the probabilistic power of each individual word as a clue.
And like any good detective, ours needs to know how to weigh the evidence. It doesn't deal in certainties, it works with probabilities. Every word becomes a clue, and our detective's job is to figure out how strongly each clue points towards spam versus ham.
Before looking at a single clue, our detective needs a starting point. In the world of probability, this is called the prior odds. It's our baseline before any evidence comes in. For simplicity's sake, we'll just assume that any new email has a 50-50 chance of being spam or ham, which gives us prior odds of 1 to 1.
Okay, let's say our suspicious email contains the word million. How much weight should our detective give this single clue? We can't just guess, we have to calculate its power based on past data.
First, we look at our database of known spam emails. It turns out the word million appeared 156 times out of almost 96,000 total words. That gives it a certain frequency in spam.
Then, we do the exact same thing for all of our good ham emails. Here, million is much rarer, appearing only 98 times in over 300,000 words. So we know it's way less common in legitimate messages. Now for the really cool part. We compare the two. We divide the spam frequency by the ham frequency to get something called the likelihood ratio. For the word million, that ratio is 5.1. This number is the power of our clue. It means the word million is 5.1 times more likely to show up in a spam email than in a ham email.
We can do this for every single word. This table shows beautifully how different words act as clues. Million points towards spam with a strength of 5.1. But look at ad click. That's a huge red flag, over 53 times more likely in spam. On the other hand, a word like conferences has a ratio less than 1, which means it's actually evidence that an email is ham.
Okay, our detective is trained, has the prior odds, and the list of clues is ready. It's time to solve a new case. Let's see how this all comes together, word by word.
This is the message we need to classify. Just 4 simple words. And remember, we're starting with our baseline assumption, 1-to-1 odds of spam versus ham.
First word up, million. We take our starting odds of 1 to 1 and multiply it by its likelihood ratio, 5.1. Instantly, our odds shift to 5.1 to 1 in favor of spam. The scale is already tipping. Next word, dollars. Its ratio is 0.8, which is less than 1. So we multiply our current odds of 5.1 by 0.8, and the odds dip slightly to 4.1 to 1. This was a tiny piece of evidence against it being spam, but the case is far from over. And now for the smoking gun. The next word is ad click, with that massive likelihood ratio of 53.2. We multiply our current 4.1 odds by 53.2, and the odds just skyrocket to an incredible 218 to 1 in favor of spam.
That was the game-changing clue.
Finally, we process the last word, conferences, which points toward ham with its 0.3 ratio. This brings the final odds down to 65 to 1. But even with that last piece of counter-evidence, the case is closed. This message is, with overwhelming certainty, spam.
So our naive detective, by treating every word as a separate clue and just multiplying probabilities, solved the case. And this brings us to a really important idea in statistics in AI.
This famous quote from the statistician George E. Box perfectly captures the spirit of the Naive Bayes Classifier. Is its assumption that word order doesn't matter technically wrong? Yes, absolutely. But is the model incredibly useful for tasks like spam filtering? You bet it is. It's a perfect example of a clever simplification that works brilliantly in practice.
So why does this simple detective matter so much? Because it beautifully illustrates a core principle of modern AI, embracing uncertainty. Instead of needing hard, rigid rules, it uses probability to weigh evidence and logically update its beliefs, clue by clue. This elegant, simple approach is so powerful that it's used in countless real-world applications, proving that in AI, the smartest solution isn't always the most complicated one.
And that leaves us with a final thought that ties back to the broader theme of our course. The Naive Bayes Classifier wins by making a clever, simplifying assumption. It's a kind of intelligent simplicity. So my question for you is, where else in the world of AI do we see this principle at work, where we solve incredibly complex problems, not by being more complex, but by being intelligently simple?